This presentation is Intro to Electricity Part 3. We're looking at circuits and configurations of circuits as well as calculations centered around circuit structure. So circuit configurations can be carried out at two primary ways: the series circuit and the parallel circuit. Series circuits have the components connected end to end, and there's only one single path for a current to flow. So for instance, if this happened to be a battery, then the current leaving the battery is going to move along the positive route. It has to go through this component, whatever it might be, and then through this to get back to the negative side. So our current has to flow through every component. These components could be, as we say down here, resistors, could be batteries, capacitors, light bulbs, diodes, LEDs, or all sorts of things that could be in the actual circuit. In a parallel circuit, if this is our battery that we have here as this component, we're going to have current leaving this side, hits this point, and then it can go in multiple directions. It can go this direction or this direction. When it hits this one, it can go in this direction or this, and of course this current is going to eventually come around in this direction. They all merge back together over on this side. So in other words, there's 1, 2, 3 paths for the current to take rather than just one. Any current that passes through this component will not pass through this component, and any component that passes through this one will not pass through the other two. So some important circuit rules, some equations that I recommend that you make sure that you have written down somewhere, or look to your PLTW equation page to make sure that you have them there. For series circuits, we have, remember, I stands for current, so this is current. In this case, for series circuits, the current is the same everywhere in the circuit. No matter where we look, we'll have the same current. Measured in amps. The voltage, the total voltage, is equal to the sum of the individual voltages. As charge drops through, or as current drops through each individual component or through a resistor, the end result is that it's like walking down steps from high energy to low energy. You're taking a certain amount of the voltage away, so to speak. So the sum of the individual voltages that the current steps through in the circuit equals the total voltage of the circuit, which is usually the battery or the source. Then we have Req. This is the equivalent resistance. The equivalent resistance, or the total resistance for a circuit, is going to be the sum of the individual resistors or resistances. Okay. We also have a major law in physics, Kirchhoff's voltage law, KVL. It says the sum of the voltage drops in a series circuit equals the total applied voltage. That's just referring to this one. Okay, in parallel circuits, in this case, our current is going to be split, and we're going to have the current through the individual pathways. If we sum those together, we end up with the total current in the circuit. And Kirchhoff's current law says that specifically that the total current in a parallel circuit equals the sum of the individual branch currents. And we end up with, for voltage, the voltage is the same everywhere. And for resistance, we've got a reciprocal arrangement where 1 over the equivalent resistance is equal to the sum of the reciprocals of the resistances. And this will show up better in a slide where we're actually going to do some calculations. So let's go to some calculations. So a circuit that contains only one path for current flow. This is the series circuit. And you can see here that we've got our battery with its positive terminal. We've got a wire connected to a light bulb, connected to another light bulb, and eventually to the negative terminal. We've got current flowing from positive to negative, passing through the resistances or the light bulbs along the way. If the path is open anywhere in the circuit, current stops flowing. We have a broken circuit at that point, so nothing flows to any of the components. So that's important if you've got a string of light bulbs, for instance, like an old Christmas tree type light bulb. If one bulb burns out, none of them work. So with a series circuit, let's look at some characteristics of a series circuit. And this is where our equations that we summarized at the beginning come from. First of all, the current flowing through every series circuit is equal. And through every component in the series circuit is going to be equal. The total resistance, RT, is equal to the sum of those resistances. Or here's our equation that we had. This, by the way, might not show up very well. This is VR3, and this says RT. Might not show up on your video. For voltages, the sum of the voltage drops, V1 plus V2 plus V3, is equal to the total applied voltage. So the voltage at our battery, we have a 12-volt battery over here, and our voltage, VR1 plus VR2 over here, plus VR3, has to sum up to 12 volts, which is our V total. And that is Kirchhoff's voltage law. So we end up with the equation VT equals V1 plus V2 plus V to however many that we might have out here. For the series circuit shown, this is a calculation. Let's use the laws of circuit theory to calculate the following. Total resistance, the current flowing through each part, I1, I2, I3, the voltage across each component, and use the results to verify Kirchhoff's voltage law. Okay, again, this is VR3, and this is RT. All right. So the solution, and actually it shows you the diagram here. So we've got our battery, we've got a resistor. This is the symbol for a resistor. We've got another resistor and a third resistor. This is showing IR1, that's the current passing through resistor 1, the current passing through resistor 2, and the current passing through resistor 3. RT is the total resistance, VT is the total voltage. And we also have voltages recorded, VR1, VR2, and VR3 for the voltages in the individual resistors. We also have this symbol over here, which is a ground. Okay, so our total resistance. According to our earlier equation, the total resistance is the sum of the individual resistances. So that means we're going to sum up the R values for each of these. These values are given in either ohms or kilo ohms. Okay, so for this one, we've got 220 ohms plus 470 ohms, 220 plus 470, and then plus 1.2 kilo ohms. RT then is 1900 ohms, or 1.9 kilo ohms. One thing that has been skipped in this slide, and it's important for you to recognize, is that we have different units. We have the ohms and they have the kilo ohms. The kilo ohm is 1,000 ohms. So if we have, for instance, 220 ohms, and we want to convert that to kilo ohms, we've got 1,000 ohms equals 1 kilo ohm. So that's 220 divided by 1,000 is 0.220. So all of these have been converted, if we're going to the final answer in kilo ohms, to 0.220, 0.470, and 1.2. All of these would be in kilo ohms. And the end result would be that we would end up with 1.9 kilo ohms. But if we had 1.9 kilo ohms and we wanted to find out the number of ohms, then what we would end up doing is canceling kilo ohms, going to ohms, and this is 1,000 ohms to 1 kilo ohm, and this is going to be 1,900 ohms. This, in most cases, for further calculations, is probably going to be the one that's preferred. This one is done more for convenience. Okay, so let's look at the current flowing through each component. So we have our total resistance. To get the total current, we're going to divide the total voltage by the total resistance. So that's the reason we found resistance first. So, and this is Ohm's law that we covered in the previous video. So in this case, what we've got is a total current equals 12 volts divided by 1.9 kilo ohms to give 6.3 milliamps. Now, this also has a little bit, maybe is jumping a little far in terms of units. Generally speaking, total current is equal to a total voltage divided by a total resistance. This total current, IT, is equal to the total voltage, which is 12 volts, 12V, divided by a total resistance, which should be technically in ohms. So we're going to divide by 1,900 ohms. This gives to be 0.0063. And the unit for this, volts divided by ohms, is amps. So this would give us amps. Now, milliamp is fine. And we would just move our decimal to the right 3 places to get what it would be in milliamps. But if we wanted to convert that, we would have 0.0063 milliamps. And using your dimensional analysis, milliamp, this should be 0.0063 amps. So we want milliamps over amps, and one of these is 1,000 of these, so that's going to be 6.3 milliamps. But they're represented as MAMP, but MA is also fine. Probably more appropriate. So since this is a series circuit, we have total current is equal to I1 plus I2 plus I3, which is our 6.3 milliamps would be our total. This would be just as appropriate to write as 0.0063 amps, or 6.3 times 10 to the negative third amps would be fine as well. All right, let's now look at the voltage across each component. We've got, we'll actually have to find the voltage across each individual one. So we've got V1 is equal to I1 times R1. Okay? And we got our initial voltage of, I'm going to go with what I would expect. And notice that they're using some extra digits out here. These extra digits are digits that would have been recorded from the calculator but were rounded on previous slides. I'm going with 6.3. This would be amps times 220 ohms equals 1.397 volts. Keep in mind that the answer that's given here, the 1.397 volts, did not come from multiplying these two numbers together. This gives if you multiply 6.349 times 220, it actually gives 1,397 volts. And it would not be volts, it would be some other unit, which would actually be kilovolts, and then, or millivolts, excuse me. So M volts would be 1,397. Then converting that to volts, we end up with the answer that they gave originally and the answer that I have here. The slide produced by Project Lead the Way is leaving a lot of metric conversion out, which may lead to some difficulty for you. So I'll try to adjust the units as I go. The voltage through number 2, which is here, VR2, is going to equal, remember the current's the same everywhere, so we have the same scenario, 0.0063 amps times 470 ohms is equal to 2.9484 volts. And to make this calculation a little more correct, that would be 2,984, and this would be kilovolts. Then we have the same thing through R3, which is here. We've got 0.0063 amps times 1,200 ohms equals 7.619 volts. So again, kilo ohms here and milliamps. It's not obvious when you look at these that milliamps times kilo ohms leads to volts. And then let's verify Kirchhoff's voltage law. Vt equals V1 plus V2 plus V3. We have 12 volts total. This is through R1. This is through R2. This is through R3. So the voltage across R1 is this value, across R2 is this value, across R3 is this value, and they all add to at least to a whole number to 12 volts. All right, in a parallel circuit, this is a circuit that contains more than one path for current flow. And if a component is removed, such as this, it is still possible for the current to take the other path to reach the component. So it can't go this way, but it could still go through this way. So this bulb will stay lit when this one is removed. So let's look at the characteristics of a parallel circuit. We've got the voltage across every parallel component is equal. And that makes sense if you realize that as we go from the positive side to the negative side of this battery, we're changing our potential energy by 15 volts. It's not exactly correct the way that I said that, but 15 volts is the potential energy change. Every time I go from one side of a resistor to the other, I'm technically going from the positive side of the battery to the negative side of the battery, which is a 15 volt difference. So across each of these, we're going to have 15 volts. So that means VR1 is 15, VR2, 15 volts, VR3 is 15 volts. This is probably filled in later somewhere else, but I'll do it now as we're thinking about it. For the resistance, the total resistance is equal to the reciprocal of the sum of the reciprocals. Okay, so 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3, etc. The sum of all the currents in each branch, the current through this branch plus this branch plus this branch, is equal to the current total to begin with. This is Kirchhoff's current law. Okay, so an example. For the parallel circuit shown, use the laws of circuit theory to calculate the following. And we want to get total resistance, voltage across each component, current flowing through each component, and then verify Kirchhoff's current law. All right, so we've got 15 volt battery. We've got an R1 470 ohms, R2 of 2.2 kilo ohms, and then we've got 3.3 kilo ohms for resistance 3. Okay. Our total resistance is going to come from this equation. We could also write 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. Let me erase that. I actually prefer the version that I wrote, but that's fine. It leads to the same point. So this gives 1 over 470 ohms plus 1 over 2.2 kilo ohms plus 1 over 3.3 kilo ohms, and that's all over 1, and that gives 346.59 ohms, or 350 ohms total. Now keep in mind these kilo ohms, this number should be 2,200 ohms. This should be 3,300 ohms. And technically the units should be the same when you're adding. So the unit conversions still have to be done. The voltage across each component next, we've got V total equals V1 plus V2 plus V3, and we've already said that's 15 volts across each of the individual voltages, or across the individual resistances. So the current through each component, I1 is going to equal the voltage across 1 divided by the resistance of 1. We've got 15 volts across each resistor, so 15 volts divided by 470 ohms is going to give us 31.915 or 32 milliamps, which would really be 0.031915 amps, and then we're moving it 3 places to the right to get milliamps. We have I2 is voltage 2 divided by resistor 2, and that's going to be 15 volts divided by 2.2 kilo ohms, or technically 2,200 ohms, and that's going to give 6.8 milliamps. And then we've got I3, voltage 3 over resistor 3, and same scenario, we get 4.5 milliamps as the final answer. So total current is going to be the total voltage divided by the total resistance, and that would be 15 volts divided by a total resistance of 346.59 ohms. That's unrounded, and that gives these values approximately 43 milliamps. Verifying the current law, we would add all those milliamps together, and we end up with 43.278 equals the current across each of the individual resistors, and that leads to 43 milliamps is equal to 43 milliamps, no matter how you look at it. So in a combination circuit, what would happen if you removed light 1? In a combination circuit, we've got these components out here, these two together, are in series to this. So we've got a series section, and then at this point we can divide in 2 different directions. But everything has to pass through this one component, and then it has a choice of light bulb 2 or light bulb 3 before returning to the negative side. So what would happen if you removed light number 1? Okay, well, let's think about this. If we've got current flowing like so, what would happen to the circuit if you break it at number 1? Well, if you break it at number 1, there's no way for the light, for the current to get through the circuit at all. So for light number 1, we would have a break the circuit. Nothing would light. If you removed light 2 or light 3, if you remove light 2, then current can go through in this direction and actually make it through by going through light bulb 3 and make it all the way back to the battery. Same thing if you were to take 3 out. If you take 3 out, then the current can go through light bulb 2 to make it through. Right, and we should probably also talk about, although I'm not going to do it right at this moment, we'll experiment with it a little bit, what would happen to the brightness of the bulbs. Okay, so if you were to take out, well, if you take out this circuit, this bulb out of the circuit, then everything goes out, so there is no brightness. None of the bulbs are going to be lit. But if you took number 3 out, you're switching from a parallel circuit component or circuit area to a series circuit, and that's going to have an effect on the brightness, relative brightness of the bulbs. We'll experiment with that. All right. Electrical power is most directly related to the amount of current and voltage within a system. Power is measured in watts, and from an equation viewpoint, power equals I times V. Power equals current times voltage. And if we're looking at current times voltage, this is amps times volts equals watts. And that completes this presentation.